Okay, let's go ahead and get cracking on this mass balance. Very similar to mass balances we've seen in the past, with a few exceptions. Similar in that we've got a rougher flotation cell, we've got a cleaner flotation cell, we've got a scavenger flotation cell. We've got a new feed stream entering the system, includes both solids and liquids, and we've got a grade of mineral. In this case, the mineral is molybdenite, MOS2. We're interested in the molybdenum metal value. That stream has 30 weight% solids, which implies right off the bat that there's going to be 70 weight% solids. I said 30 weight% liquids, I think I said, but I meant 30 weight% liquids and 70% solids then in a slurry form. The cleaner concentrate is also this final system concentrate. It has a metal grade of 0.3% molybdenum, 70 ton per hour water. The tailing has a total solid weight of 355 ton per hour solids. One little bit of difference here is this upper portion of the circuit. There's a ball mill, which is very common. It's added to a circuit to regrind the mineral, liberating it. If it turns out that some of the minerals aren't liberated well enough, we can't concentrate them, so we put in what's called a regrind circuit to reduce the particle size of those minerals that are too large to be concentrated. You can see the solid flow into that system is 35.4 ton per hour solids. There's a classifier after the ball mill, and the classifier does exactly what the name implies. It classifies the particles in terms of size. Those particles that are too large are sent back, recirculated into the ball mill for further regrinding. Those that are small enough size-wise to be recovered go to the overflow. Key point here is that there's really only one solid flow into the ball mill. So this is an entrance, let's call it. And there's only one flow out. This is an exit. And so what that means is all of these solids, 35.4, are going to report over here. Now they're going to be smaller particles, but they're still going to weigh the same and they'll have the same grade. There is a makeup classifier feed coming into the classifier. That is just water, no solids. So once again, the solid and grade does not change as you go from one side of the ball mill new feed over to the overflow out of the classifier. So with that said, let's go ahead and get started. As we've done in the past, we will try to characterize the system on the flows into the system and the flows out of the system. And then as we do that, after we do that, we'll start making our way inside and completing these internal unit operations. So let's start as we normally do with the new feed and characterizing it. Once again, there's 400 ton per solids. There's a mineral grade of 0.06, 30 weight% liquid, and 70 weight% solid in that new feed. So I've tried to isolate that feed with those known values. I'm going to call X the ton per hour slurry, and by slurry I just mean solid plus liquid. And if the weight fraction solids is 70% or 0.7 weight fraction, I can take X times that value and set it equal to my solid weight, and calculate a slurry weight of 571.4 ton per hour. And once I have that, I can subtract the solid value to get at my liquid. And so now I know that my liquid weight is 171.4 ton per hour solid, or ton per hour liquid, just by taking slurry minus solid to get the liquid. I need to calculate the weight fraction metal in this new feed stream. And I can do that by taking the mineral grade of 0.06 times the molecular weight fraction of molybdenite. And so I take the molecular weight of molybdenum divided by the molecular weight of molybdenum plus 2 times the molecular weight of sulfur, recognizing that my mineral is molybdenite. And so that's where that 2 comes from for the sulfur. And so these are just molecular weights here that were given for both molybdenum and sulfur. And I multiply that by my mineral fraction that was given of 0.06, and I end up with a molybdenum grade in the feed of 0.037. Of course, the train is going to start blowing as it normally does, but we'll power through that. It won't last long. We're going to take this grade of molybdenum, convert it to weight fraction, multiply it through by the total solid to give me the weight of molybdenum in my new feed of 0.146 ton per hour molybdenum. So let's jump back out. We've been able to characterize that new feed stream. Next, let's look at this cleaner concentrate stream, which is also the final system concentrate stream. And we're recognizing we've got a grade of molybdenum given there of 0.3 weight percent and 70 ton per hour water. And our total tailing weight is given along with the new feed given values and that classifier makeup water of 3 tons per hour. So let's go ahead and focus then here on this cleaner concentrate stream. Here it is. And we're going to focus on the concentrate stream. 400 is the ton per hour solids in new feed. 355 was the ton per hour solids in the tailing. Probably worthwhile looking at that mass balance to see where those values came from. Inflow, there's no solids here. Outflow, we have the tailings. So the difference between the new feed and our tailings are the solids in the cleaner. So that's where those values of 400 and 355 come from, giving us 45 ton per hour solids in the cleaner concentrate. This is just an appendage from earlier, since we already know the water is given here. We don't need to calculate the slurry, but we can calculate the amount of molybdenum in the cleaner concentrate by taking the weight percent or the grade of molybdenum, converting it to weight fraction, and multiplying that by the total solid weight gives us 0.13 ton per hour molybdenum in the cleaner concentrate. So if we look at our system again, there's really only one concentrate being produced here, and if we know the molybdenum in our new feed, we should be able to calculate an overall system recovery at this point. And we can do that by taking the cleaner concentrate, molybdenum, divided by the molybdenum in the new feed, which we calculated earlier, times 100, gives us an overall system recovery of 92.5, which is quite reasonable value for the overall system recovery. So we've calculated or characterized a couple streams now. Let's move on to the tailing. This will be our third area of interest. keeping in mind that we're given some values in terms of the total weight of the tailing being 355 ton per hour, plus some values that we were able to calculate along the way for the new feed as well as the cleaner concentrate. And those are the one feed in that contains solid and the other feed that out that contains solid. So looking at this tailing here, let's do a water mass balance. 3, of course, was the classifier overflow. $171.4 was the water in the new feed. 70 was the flow out. So these two are water flows in. The 70 was the cleaner concentrate water value. And we're left with 104.4 ton per hour leaving the system in the tailing. Getting a little messy here, and I apologize for that. I'm going to calculate the ton per hour molybdenum in the tailing. The 0.146 was in the new feed, the molybdenum in the new feed. 0.135 was molybdenum in the cleaner concentrate. So the difference then is what's exiting the system in the tailing, or 0.011 ton per hour molybdenum in the system tailing. I can get the grade of molybdenum in that tailing by taking the weight of molybdenum divided by the total weight of solids, which is given of 355, giving us a tailing grade of 0.0031%, which is very low grade, which once again is expected because this is our final system tailing. So we're making good progress getting these external streams all characterized. So now it's time to start moving inward. Let's look at the feed to the scavenger flotation, recognizing that the recovery is 69%, total solids 5 ton per hour. If the recovery here to the concentrate is 69%, then the non-recovered material to the tailing is some 31% of this feed. That'll come in handy here. Especially would also come in handy as we've already characterized this stream, this tailing exit stream, which is also the scavenger tailing. So we're looking at that scavenger cell, once again, 5 ton per hour in this concentrate, 69% recovered, 31% not recovered. So we can, and we also calculated earlier in this tailing stream, the ton per hour molybdenum was equal to 0.011. Knowing that value, we can divide by the non-recovered fraction, 31%, converting it to a fractional value, divide the tailing amount by that fractional value to give us the ton per hour molybdenum that was present in the feed to that cell, or 0.035 ton per hour. The ton per hour in that feed is equal to the 5 ton per hour exiting, plus the 355 that's exiting into the tail that was given, or 360 ton per hour total solids. So the grade then of molybdenum in that feed is the weight of molybdenum, 0.035, divided by the total solid weight of 360 times 100, or the feed grade into the scavenger cell is 0.0097%. Just checking off the progress we've made. Next, let's go to the scavenger concentrate, which hopefully makes sense because we've characterized the stream in the feed, in the tailing. Let's move on to the concentrate. So we've got the feed done, we've got the tailing done. Now we want to focus on that scavenger concentrate stream, and we can because we've characterized both the feed and the tailing, we can take the weight of molybdenum in the feed minus the tailing to give us the weight in the concentrate, which is equal to 0.024 ton per hour. We're given that there's 5 tons of solid there, which allows us to calculate the grade of molybdenum in the scavenger concentrate stream. And that's equal to 0.024 divided by 5 times 100 gives us a value of 0.48 concentrate grade coming out of that scavenger. So we're doing pretty well here. We've characterized a lot of these streams already. Next, I want to talk a little bit again about this classifier overflow and the notion of kind of drawing an imaginary line and looking at what's flowing in and what's flowing out in terms of the solids. So here it is again. There's grinding being done there in the ball mill. Particle size are being reduced. There's classification going on. There's some solid weight and slurry percent as well there. But that really doesn't concern us here because we're only looking at what's coming in, what's going out. And we know there's some water added, but this solid shows up over here, and the grade is going to be the same. So that's what I'm just trying to show, that those two feed streams are the same, and the solid is 35.4 ton per hour. Now, I don't know the molybdenum grade yet, but it'll be the same over here when I do know it, but I haven't calculated that yet. Okay, let's go on then. Next, let's look at this combined feed into the rougher. And I say it's combined because we've got this new feed joining the overflow into the rougher. I'm just going to make a note of the streams that we've kind of begun to characterize. But let's look at this feed into the rougher, noting that there's an 85% recovery into the concentrate. That means there's 15% lost into the tailings of the rougher, which is also the feed into the scavenger. So here's our rougher cell, and we're interested in this combined feed stream here, 85% recovery. The combined feed is total solids 400 in from the new feed, and that 35.4 ton per hour in the classifier overflow, giving us a total combined feed of 435.4 ton per hour solids. Now, we'd calculated the scavenger feed, which is also the rougher tailing earlier, and we calculated that there's 0.035 ton per hour molybdenum in that stream. Why is that significant? That's significant because we have a recovery here, and that 0.035 represents a 15% that is non-recovered. So we can take that value divided by the fraction non-recovered to get us the feed amount into the rougher, this combined rougher system, or 0.233 ton per hour molybdenum is contained in the solids. We can get a grade of molybdenum by taking that weight of molybdenum divided by the total solids times 100, giving me a feed grade, combined feed grade into the rougher of 0.05% molybdenum. So we're doing pretty well. Just checking off the streams that we've characterized. Next, let's go to the cleaner feed, which is also the rougher concentrate, and characterize that. So here's our cleaner cell. We've got our feed, our concentrate, and our tail. We've already done a good job of characterizing that concentrate early on. The total solids here are represented by the feed in, and this is coming from our rougher cell, where we had 435.4 coming into the rougher previously, and 360 leaving the rougher and feeding into the cleaner. So this value should be 435 minus 360, giving us the feed into this cleaner cell. 75.4 ton per hour fed into the cleaner cell. The ton per hour molybdenum is also, once again, the rougher feed minus the rougher tail gives us the rougher concentrate, which is the feed that goes into the cleaner of 0.198 ton per hour. And we can get the cleaner feed percent molybdenum by taking the total weight of molybdenum divided by the total solids and multiplying by 100 to get a grade in this cleaner feed of 0.263%. So just calculated that. Okay, next let's look next at the cleaner tail. Looking at the cleaner tail, there was 75.4 tons fed in. There was 45 tons in the cleaner concentrate, giving us a total solid value of 30.4 ton per hour solids. There was 0.198 molybdenum fed in. There was 0.135 molybdenum in the concentrate, giving us a total molybdenum value in the cleaner tail of 0.063. We can calculate that the grade of molybdenum divided by the total weight of molybdenum divided by the total solids times 100, or the grade in that cleaner tail of 0.207. Just checking off all the streams we've characterized here. So we're really left with a little bit to do here in this getting the grade and the grade in that ball mill new feed, which is a combination of the cleaner tail and the scavenger concentrate. So let's go ahead and do that. Divided this into two parts. First, looking at this combined stream, we know that there's 35.4 total. The molybdenum from the two streams is shown here that are feeding it, the scavenger concentrate, and the cleaner tail. Weights total 0.087 ton per hour molybdenum, and we know we're given that weight, total weight, so we can calculate that the grade here in the ball mill new feed is the weight of molybdenum, 0.087, divided by the total solid weight of 35.4 times 100, giving us a grade of molybdenum in the ball mill new feed of 0.245. Now, down below, back to this notion of the overflow from the classifier, we'll have the same solid weight, the same amount of molybdenum, and the same molybdenum grade. The only difference is that these will be finer particles. Here, because of the regrinding that's being done and the classification. And so I think that completes all of the calculations to complete this circuit.